Welcome everyone to this lesson on slope fields. Now that you have seen how to analytically or algebraically find the equation of a function from that of its derivative by using antiderivatives, we turn now to a geometric approximation of a solution by the use of a slope field. A slope field is the graph of a function obtained from that of its derivative. You may also hear it referred to as a direction field. Slope fields enable us to graph an original function without actually solving it algebraically. This is very helpful if it's an equation of which you cannot take the antiderivative. Here is a more formal definition of a slope field. A slope field is the graphical representation of the general solutions, a family of functions, to a differential equation. It is a graph of short line segments whose slope is determined by evaluating the derivative at the point. So what does a slope field look like? The way in which these little slope cuts, as we call them, are determined is by substituting into the differential equation the x value from the graph, because this differential equation only has x's in it. That's why we would be substituting x values. From that, we would obtain the slope at that particular x value. Notice that for any given x value, see how as you go vertically from along that x value, the slope cuts are all parallel to each other? That's because this differential equation is only dependent upon the x value, not the y. So for any given x value, every place along that vertical x value, those slopes are all going to be the same. Let's talk about the connection between a slope field and a possible solution for that differential equation. Consider the function f of x equals x squared plus c. You see it graphed here, and the plus c, of course, would vary the height of that parabola in the plane, and that's what you see represented here on the graph. The slope field for this family of functions is drawn by sketching slope cuts to the curves at various x values. It is the slope field for the differential equation dy dx equals 2x. And if you take the derivative of that original function, you do get 2x. The way in which these slope fields are drawn, let's use the red curve as an example. If I were to pick right here at the bottom of the parabola on the red curve, where x equals 0, that's the bottom of the parabola. The slope there we know to be 0. So there would be a horizontal slope cut there. If I go a little bit to the right, maybe around where x equals 1 on the red curve, and draw a little slope cut. See the little blue slope cut right on top of the red curve here? That's representative of the slope at x equals 1. If I keep going up here to maybe where x equals 2, and draw a slope cut, you'll notice there's no slope cut exactly right there on the red curve, but there are some parallel to it right there in the same area. If I go over here to about -1 as my x value and determine the slope there, you can see the little blue slope cut right here, lying right along the red curve where x equals -1. Again, if I go over to x equals -2 and determine the slope there, there's no blue slope cut drawn right there on top of the red curve, but you can see it's very close in proximity to these other two that look like they have that same slope that we would have on the red curve at x equals -1. You have a graphing calculator program that will draw slope fields for you. You would want to start by setting your graph to zoom decimal, which is zoom 4. Zoom decimal window simply provides for a bit clearer slope graph. You can, of course, set it to something else of your choosing, though. Under y1, you will want to enter your differential equation, dy dx. If there happens to be a y variable in the differential equation, simply type the y in by using the alpha function on your graphing calculator. The slope field program is written to allow for this. You then would run the slope field program, and you will see your slope field drawn for you. When you're finished, do remember that your slope field graph needs to be cleared out, and you do that with the clear draw command on your graphing calculator, which can be found under the draw menu, and it's the first option there. Let's try a couple of these using the slope field program on our graphing calculators. Remember, you will want to begin by setting your window to zoom decimal, zoom 4. If you go under y equals, let's graph the slope field for the differential equation x over y. The y, as I mentioned, you can simply bring up by using your alpha function, and you simply have to hit alpha and then hunt and peck for where the y is. Once you have that entered, you can back out of it and pull up your slope field program. Remember that your programs are alphabetized. And hopefully your slope field looks like this. Let's try another one. Remember, we'll want to clear this out first. You do that by hitting second program. You'll notice it says draw over it, and the first option is clear draw. And you'll notice all your slope field cuts go away. If you go back under y equals, let's try an exponential function. Let's do e to the x. Back out of it, and then run your slope field program. And your slope field should look like this. If you think about what the graph of e to the x looks like, you can start hopefully visualizing in your head what solution curves through this slope field would look like. Recalling what the typical e to the x graph looks like, remember up here in the first quadrant, it rises very sharply, as is indicated by these almost vertical slope cuts here. That's almost indicating you have a vertical asymptote of sorts. And if you think of what the e to the x graph looks like, it starts over low to the negative x-axis, it cuts through the y-axis, and then it starts rising up. So if you think about it, the graph itself of e to the x will follow the line as indicated by these slope cuts. Let's try one simply in terms of y now. Let's clear this out. And we're going to graph the differential equation y times the quantity 2 minus y. You can back out of it and then run your slope field program. This is a slope field that, because it is only in terms of y, as you were determining the slopes at each of the points on this graph in the plane, you would be substituting, of course, only y values, as this differential equation is dependent only upon the y. Because of that, for any given y value, you'll notice that these slope cuts are all parallel to each other going across. So for instance, up here at around y equals 3, going straight across through there, you'll notice all those slope cuts are pretty much parallel to each other. Same thing down here at this looks like maybe y equals a negative a half. They're all about parallel to each other. Up here at y equals a positive a half, 1 1/2, they're all parallel to each other going across.